DC? Sample and hold. What's the second one? Comparator. Plus or minus over here? The control circuit, and then the SAR logic. 1, 2, 3, 4. Assuming it's a 4-bit, it's a DAC, and feed it back to the inverting. Okay. So, for example, it's a 10 volts as a range of the DAC, right? Or for the whole circuit, it's 10 volts VDD, and I'm inputting a 4.5 volts analog. It's going to be on the quiz on Monday. Okay. I'm asking you to draw all the state diagrams. So first of all, you got 4 bits as the resolution of the ADC, and you need how many states in there in total? 4 plus 1, right? It's always n plus 1. So 5. Okay. Now you start drawing it. I'm going to give you a random voltage input and tell you this is 10 volts, and ask you to draw all the timing diagrams and all the converted results, analog output overall from the DAC. So 10 volts at our beginning. What's the digital code in here to be put in here? The start state is what? 1 and 3 zeros, right? And that's going to be 5 volts. So this will be, the voltage here is the VDAC, 5 volts. And here is being held as 4.5 volts. That's V in, that's VDAC. So immediately you know that V in is less than VDAC. Because this is 5 volts, right? This is 5 volts. So what the output would be over here? Five volts. 4.5. What's the output? That's a fish memory. You were really good at it.
0.
Yeah, 0. Okay, so 0 means you want to put the 0 where? Yes, 0 here, right? And shift everything here to the right. So that will be fed back here, and this is 10 volts divided by 16 times 4. Is that right? 2.5 volts. I mean, you can write a 2.5 volts inside of the circle here. Yeah, 2.5 volts. So 2.5 volts, and then you know that V in is larger than VDAC. So you need a 1 after that, right? So this is newly plugged in. And then you need 0, 1, plugging a 1 here. And 1, 0. And this is 10 volts divided by 16 times 6. And that becomes 3.75. So still, V in is larger than VDAC. So that was a newly plugged. And then the next one, still 1, right? 0, 1, 1. And this being shifted to the right, you're getting a 1 here. It's 10 volts divided by 16 times 7. 4.375. V in is still larger than VDAC. Now we reach the last one. That was 0, 1, 1, 1, right? 4.375. This is 10 volts divided by 16 times 7 again. So we'll stop here. Not making any further improvement. Let's thing is already shifted out, so it's not doing anything anymore. So eventually the final result is 4.375 volts. This is pretty okay, I think, compared to 4.5. That's why it's called successive approximation register, right? Successively approaching that final result. Would you be ready for the quiz on Monday for this? Just study this, okay? Study this over the weekend or later today. Make sure we can get a full credit for this kind of question. All right. So now we are talking about how to implement the circuit. It includes several things. The first one is called a code register. I'll do this really quick, okay? Remember here, you got a S, R, you got a D, you got a Q, Q naught, and here's the clock. Okay, if I give a 1, this is called active 1, right? Active 1. Or active 0. For this one, it's active 1. Wait, active 1 or 1 active? I forgot. What's the term? Is it active 1 or 1 active? Whenever you put a 1, you activate it, right?
Yeah.
I'll figure that out. I forgot. 1 active. Active 1. Active 0. I think active 1.
Yeah, be active 1.
True, active 1. Yeah, active 1. So this is active 1 because there's no bubble here, right?
Yeah.
So if you put a 1 here, you reset it. If you put a 1 here, you reset it. But you are not setting and resetting at the same time, all right? But if you are giving zeros to both, what's going to happen? Zeros to both.
Then it's going to be D flip-flop.
It's going to be D flip-flop. So you are 0 for both. It's not setting or resetting, which is fine because it's going to be D flip-flop. So for D flip-flop, at the rising edge, because there's no bubble, so at the rising edge of the clock, D will be sent to Q. Okay? That's how that works. So for the code register, we assume that we are using these type of D flip-flops, SR, and these are, that's a D, right? D. And here's a Q, Q naught. And for the Q, I'm sending the result to the as the output here. And I'm feeding that comparator's output. Because remember, all these code being registered into the SAR block, these are actually the comparator's output. Remember, if the comparator's output is 1, we register that 1 over here. If the comparator output is 0, we register 0 here, right? So that's actually the comparator's output. So in that case, the comparator's output are being used as input or the D's for the D flip-flops of the SAR block. And we name this output as comparator CUMP, right? Just for short, CUMP. So this code register is part of the SAR block. So I'm introducing the circuit for the SAR block. I'm designing the circuit for the SAR block to implement this algorithm right now. Okay. So code register is the first thing we need for the SAR block. First thing we need for the SAR block. So for this guy, it looks like this. And we assume that there's another block on the top. We'll shift ones from left to right. And it's giving a 1 and O0 at the very beginning. And it's able to shift that 1 to the right sequentially. And we don't know what the circuit looks like. I'm going to introduce that circuit later. But now let's assume it's going to happen. Okay, this is going to happen. All right? Assume this is going to happen. And these comparators output are being fed into all the D's, digital inputs. Okay, and then the Q of the next one will be used as a clock. There's a clock input for the previous one. And that's the entire circuit. Now let's see if that makes sense. So at the very beginning, whatever on the top is called a sequencer. On the top is able to output 1 0 0 0 0 to the S, to all the S of the code register. So this guy is called code register. Okay. What's gonna happen for the output? That's the entire SAR block. Comparator's output is this guy. If you ignore this control circuit, it's just directly being fed into the SAR's input, which is comparator output. And these 4 bits over here are these 4 bits output. Okay, comparator input, output, and there will be a clock for the sequencer, but we are not including that for now. So there will be a clock. You need a clock for this guy. Okay, clock. But we are not considering that for now. Just looking at this one, for example, it's part of the SAR block has a circuit called sequencer magically creating 1 all zeros and keep shifting that one to the right. But before we shift it, now let's see if that makes sense. If the comparator's output is always there, it could be 1 or 0, it doesn't matter. It's going to be always there, right? There will be something there, okay? And we put a 0 to the first S and all zeros to the rest. Definitely R is not being set, just assuming they're all zeros. We're not resetting everything, okay? But we are setting the first one at the very beginning, what the output looks like. What is the output? Because this one is being set, right?
So it's just forcing that.
It's a 1, right? And for the rest, you don't do anything. There's no input, there's nothing. But you are saying, hey, the comparator's output is being fed into D. And you are not setting or resetting, assuming this is 0. You are not setting or resetting. So it should be a normal D flip-flop. So the comparator's input to the D should be sent to Q and changing this one, so it shouldn't always be 0 anymore. Is that the case?
It'll be ambiguous because it'd be whatever the comparator. It'd be whatever the comparator is output.
But thinking about the D flip-flop I just told you guys, right? The D flip, if it's working as a D flip-flop, yes, it's going to pass D to Q, but what is required? The rising edge. But do you have a rising edge here? No, there's no rising edge. If you look at the clock input, like for example, you are talking about this one, because this is being set, right? There's nothing you can change. Okay? But for this one, you are thinking, hey, the comparator's output is being put into D, so that's a comparator's output could be 1 or 0 depending on the result. And nothing will be sent to Q because this guy's clock is a Q from the next stage. Okay? If nothing is happening here, this by default, before everything got started, this is actually a 0 here. Before you start it, right? It shouldn't have any voltages. It shouldn't have a power or charges over there. That will be magical if there's a power before you do anything, right? There won't be anything. Just 0, okay? 0. Or if it's not 0, at least it's not changing. So, which means this on this wire, there won't be any rising edges. Okay? So by default, this should be all zeros. as initial state. Trivial zeros. So what's next? What's next? So for example, I got A3 here, A3 as a current comparator's output. Okay? And I'm shifting this guy to the right by 1 bit. Does that make sense? If I have a 1 or zeros, I'm getting A3. Why? Because the first initial state is also being compared and giving you an output, which is A3 over here. This is A3. Okay, so that result already appears here because it's being compared with this initial value, and it's giving you this result. And now my goal is to register this guy to here. Okay, and now let's see if that's happening. So the thing is, you need to shift this one to the right. So what's happening is it becomes 0, 1, 0, 0, 0, because you are shifting this one to the right. The sequencer is going to do the job and putting a 0 here, but 1 here to the next stage. And what's going to happen for this state? Because this one is being shifted to the next stage, and this one is being shorted to the S pin, so it's setting this guy, and this becomes a 1. So it was 0, and now it jumps to 1, right? And because the Q here is shorted to the clock of the previous stage, so that jump, that rising edge, will trigger the clock. It's used as a rising edge of the clock for this guy, and this one becomes what? So first it's the D flip-flop because it's 0 here, right? It's D flip-flop. It's not being set anymore, and also it's receiving a rising edge. So A3, which appears that this wire will be registered to here, to Q. Does that make sense? Yeah, we register here. So what about the next stage?
Wouldn't it at the same time also set A2?
Yeah, because this one is being set. So this is being set, right? What about the next? It's not being affected. This is not being affected. It's still 0. Nothing is affecting the following stages. So there are still zeros. Okay? So we are definitely implementing this from here to here. Okay? As you can see, 1 zeros and A3 and 1 0 0 is shifting this guy to the right and plugging the A3, the comparator's output to the MSB. Make sense? And then keep moving, and you're getting the sequencer will do the job, right? So it's doing 0 0 1 0 0. What's gonna happen for this guy?
Set A2.
So let's see what's happening to this. Is this gonna change or no?
No.
Why?
Well, the state doesn't change.
So this one will give you a result for A2, right? So now at this line, it changes from A3 to A2. That's the second compared result. A2 now appears here, and then it's to the shift. So the shift will set this guy, and so this have a rising edge, right? So this one will trigger the clock here, and so this definitely will register whatever appears here, which is A2, right? Will be registered over here for sure. What about this guy?
Because set is set to 0, and yeah, the state hasn't changed since last iteration. So
But the thing is, what about A2 is the 1, then there's a rising edge here, and then we'll change it to A2. Would that be possible to trigger that clock and send whatever A2 here to this as well and change A3 since we don't want to change it? See here, it's not being changed. A3 is staying there. Would that be the case?
Yeah, they could.
Hmm?
Yeah, they could, because A2 could trigger the.
Take one more look at it.
What's the case that you're saying? Like if
I'm saying,
if
would
A2
this,
is what?
can we retain A3 to here or not? Because if this one got a 1 here, right? Got a 1 here, and we'll set this guy and rising edge here, and we'll register A2 to the Q here, right? And that A2, this output is shorted to the clock of the previous one. Is that possible that we got a rising edge here, so A2 will be registered to the first one as well? Why?
Because it either stays a 1,
Yeah.
or it's a falling edge and it goes to 0 and it doesn't trigger the clock.
Yeah. Take a look. I want everyone to get the same concept here. Did you see that? You see that? Is there a rising edge? There won't be a rising edge.
Yeah.
Either from 1 to 0 is a falling edge, or 1 to 1 there's no rising edge at all. Got that? Is that beautiful? Or oh, we designed the circuit just by chance it works.
Flip-flops are pretty cool.
Yeah, there's no rising edge. See, there won't be a rising edge. So A3 will be retained. Okay? And then 0, 0, right? And keep doing the same thing because this one is being shifted to the next and it will avoid any rising edges for the next stage so we can retain all the values for the previous one. Okay, so keep doing that, and eventually you'll get A3, A2, A1, A0. So you're asking, what is the fifth one doing here? What is this one doing?
Let's do the n plus 1. What is it? Needing additional.
Will that tell you when it's done?
Yeah, it's holding that value and eventually provide a rising, because this one needs something, we need a clock, right? So that's why whenever one is being shifted to here is providing a rising edge to register A0 to here. If you don't have the last stage, who is going to give the rising edge? You need the last one waiting there, you know, playing a certain role, you know, a supporting role to give a rising edge to the clock of the previous one for the LSB here, right? Okay. So that's a code register circuit, and now we are going to look at the sequencer. How can we make this work? And just shift the one to the right sequentially. Just record it to come back to the video if you're not getting that 100%. Sequencer. Need a, so we're talking about code registers done. Have all the pins. So the sequencer circuit are also D flip-flops. Cool. And this goes to, let me make sure it's right before I move forward. Okay. What you want to do first? What's happening first? So I'm grounding this pin so we're not setting or resetting when we don't want to do that. Okay, so make sure these are not being set. This is not being reset. Okay. So what's the first you want to do? First thing. what's the first code you want to give to the code register? 1 zeros, right? How do you make that happen? How do you make that happen? Hmm?
So
We know that if you want to give a 1 to Q, we need to set it. If you want to give a 0 to this, we don't reset it. And that's why I'm shorting the circuit in this way. So the setting of the first one is also shorted to the reset pin of the rest. So if I give a 1 0 here, I'm outputting this code. What do I need here to output this code?
I need a clock.
Hmm? Do you need a clock? You'll need it later, but not now. So you need a clock, synchronous clock for everyone. So the set and reset is not being affected by clock cycles. If you set it, it will be set. If you reset, we reset. We'll force it to set or reset. Just keep that in mind. Clock is not going to affect anything if you set or reset it. So in that case, if I give a what signal here, I'm going to set the first one, reset the following ones to make sure I'm outputting 1 or zeros. What is this called? At the very beginning.
Yeah, that's that'd be the control circuit.
No, you need just 1 digit here to set the first and reset the following ones. Here's the output. So this is the output. All these lines are outputs of the D flip-flops to be sent to the code register. If you want to set the first one, reset the following ones, you just give a 1 here because this is shorted to the set of the first one and shorted to the reset of the following ones. Here, I'm sorry. Okay, so this is this guy. Okay? So you give a 1 at the very beginning, you got this. Make sense? Then what? What's next?
Then every clock cycle will push the 1 to the next D flip-flop.
Where's the 1 to be pushed to the next?
Well, it would just push whatever's
From Q?
currently set in the first one to the next one.
Oh, from Q, yes. Right? So from Q, yes. So, but the thing is, this is still being set, right? How to do that? Now you have ones, the 1 being latched at the output, because that's a latch, it's going to store it temporarily. And all the zeros are being stored over here temporarily, right? So first you give a 1 here, you set it, and it's ready, right? For the next cycle, you put it back to 0, right? Don't set it anymore. Don't set it anymore. So if this is not being set, all the rest are not being reset as well. So these are D flip-flops. Okay, so which means at the very beginning you create a little 1 here, and then you want to keep shifting that 1 to the right. However, what is going to replace the data here? What do you need? What do you need to be replaced? What do you need to replace that 1? By looking zeros, right? So only the very beginning you got a 1, but all the rest should be zeros. So how do you make that happen?
Make sure you have a 0 on the input D.
Okay, so you set it at the very beginning, and then whenever you give a 0, you enable the D flip-flop mode, and then you just keep, whenever the clock arrives, the rising edge, because this is shorted to ground, so 0 will be passed to the Q, and also for the following ones in the following cycles. Does that make sense?
Okay. I think so.
Okay. So I'm gonna assign a homework. I haven't assigned any homework assignments for the class for 2 weeks. So there will be a homework 4, number 4, to verify the D flip-flop operation, the rising edge, and also build a sequencer and code register in electrical VLSI, okay, to verify it. Now, so we know D flip-flops are awesome. It will be able to implement the circuit as what we desired, but how to design a D flip-flop? That's the question here, right? So we need from the unit to make it work. But you can see the SAR, the entire SAR block doesn't really, it's nothing but a code register sequencer. It's pretty simple. Okay, so now we go down one more level, and we'll figure out the D flip-flop. So before you do D flip-flop, you need to know the fundamental circuits of a latch, right? The latch. Right, let's do SR latch first. So SR latch means set and reset latch. Set and reset what? Q. The Q is the output. So setting and resetting Q. So which means if you turn on S, you set Q. If you turn on R, you reset Q. Turn on S, you set Q. Turn on R, you reset Q. That's the basic operation of the SR latch. Does that make sense?
Yeah.
You give a 1, you turn it on. You turn on S, you set Q. You turn on R, you reset Q. That's the fundamental operation of it. So it will, knowing how this works will never become an issue since you understand it right now. It's called S and R because you turn on it, you set it. You turn on this, you reset it. And now, given that we don't want to, I will show you why, but we never set and reset this latch at the same time because we just want to set or reset, not set and reset. So don't abuse it. So that's why we don't, that's how we don't set and reset at the same time. We set, we don't reset. We reset, we don't set. Make sense? However, for a NAND-gate based SR latch, you could operate it under a memory mode. It's going to memorize the previous state. It's going to latch it over here. I'm going to show you why. And so the code to latch it and memorize it should be 0 or 1 for both.
Would be 1 for both.
1 for both. Why? Because the AND logic or the NAND logic, 1 as one of the inputs is not going to affect the results. It's an AND logic. 1 and something is still that thing.
Yeah.
Is that the case? 0 and something will kill it. 1 and something is still that thing. So that's why 1 is not changing it. If you are giving me a 1 1 here as an input, for example, the previous result is a Q, right? So Q is being fed back here as a Q NAND 1 is still Q naught. Q naught being fed back here is Q naught. Q naught NAND 1 is still Q. Stable. It's not changing. It's the latch. It's memorized the previous state. So for NAND gate, 1 1 as the input is not changing the result. What about 0 and 0? Zero will kill the NAND gate or AND gate. It's going to kill it. So if you put a 0 and 0 here, you are definitely getting 1 1s. The designer want to use a Q and Q naught. If you give a 1 and 1, it's not going to work. Or it's not working for that purpose, right? So it's an invalid code for the input. So what does invalid mean? We are just not using that input. It doesn't mean that it's gonna do something really bad, right? It won't cost anything seriously. It's just not creating a useful code. Just be clear on that. I mean, when I was in college, they make this case really scary. Seems like if you put a 0 0 there, it's gonna burn down the whole building, something like that. Prohibited. Whoa. Am I going to put in the jail? Or something? No. So if you know the circuit, it's just giving 1 and 1 to it, but nothing else.
Yeah.
It won't be useful, right? So, could you let me know which pin is S, which pin is R in this case?
S is the top there, right?
Why? Let's say that if we put an R here and S here, what's going to happen?
That means
So, like I said, if you set it, okay, if you set it, I want this to be 1. And now let's verify it. You turn on S, right? You want to set it, right? Let's see if that's the case. I'm trying to set it. I put a 1 to S and 0 to R, and 1 is not going to affect anything, so I want to start here because it's not changing anything. But however, this guy will kill it, so we know this will be 1 definitely, right? No matter what this is. 0 here will give a 1 here. And 1 will be fed back to here, and 1 will be 0. Okay? And 0 will be fed back here, and 0, none, 0, still 1. So stable. Is it setting it?
yes.
Yes. Is it stable?
Yes.
Yes. So the bottom one is S and top one is R. So what about NOR gate? You'll see a NOR gate. So keep in mind, I'm not telling you this is the only way to do a SR latch. Okay, for this guy. So study this over the weekends. There might be a quiz on Wednesday regarding if I give you this circuit, which is S, which is R, and truth table, and also states the output. I'm going to ask you guys to explain what's going on for the NOR gate version of the SR latch. Okay, and on Monday next week we'll start from here to start building. What's that?
So is states memory invalid?
Yeah, like these ones.
Okay.
So Monday we'll start from the latch and start building the D flip flop from this. Okay. Yeah, I think that's it. So if you receive the email from David, make sure you sign the NDA, and also get the TSMC's NDA signed as well. But put them in one assignment, right? David's and TSMC's. Even though I don't think I can still change the assignment, can I? I probably can still edit it, the description of the assignment. So I'll just let you add both the TSMC's NDA, the exhibit A and B, and also WDC's exhibit something. I don't know how many of them are there. So submit through comments. All right. Any questions? Anything? All right.
This was the best time.
This is the only time. Oh, did you do the same?